There was a time when the universe was perfectly, absolutely dark. To understand the gravity of the discovery made by the James Webb Space Telescope on this 22nd of December, 2025, we must first travel back to a period that defies our common understanding of reality. We call it the Cosmic Dark Ages. This was not a darkness born of a lack of candles or the setting of a sun, but a fundamental property of the infant cosmos. For hundreds of millions of years after the initial expansion of space, there were no stars, no galaxies, and no glowing nebulae to break the monochromatic void. The universe was a vast, cooling sea of neutral hydrogen and helium gas, drifting in a silence so profound that it is almost impossible for the human mind to grasp. It was a blank canvas, yet one with a hidden, restless energy. Within this darkness, the invisible hands of gravity were already at work, pulling together the first strands of what would eventually become the cosmic web. This period is the final frontier of modern astronomy, and until very recently, it was a place where our instruments simply could not reach. When we speak of the dawn of time, we are referring to the moment when this total shadow was finally pierced. The first stars, often called population 3 stars, were unlike anything we see in the modern night sky. They were titans of pure hydrogen and helium, hundreds of times more massive than our sun, burning with a fierce, violet intensity. They were the pioneers of light, and their arrival changed the chemistry of the universe forever. However, because they lived fast and died young, their existence remained purely theoretical for decades. Astronomers knew they must have existed, for without them, the heavy elements that make up our bodies, our planet, and our technology would never have been forged. But finding them was a task that felt almost hopeless. The light from these first suns has been traveling for over 13 billion years, and during that time, the very fabric of space has expanded, stretching that light until it is no longer visible to the human eye or even the most powerful optical telescopes. This brings us to the significance of the James Webb Space Telescope. It was designed specifically to be a time machine, a tool capable of seeing into the infrared spectrum where this ancient, stretched light now resides. For years, scientists waited for a signal that would confirm their theories about the earliest moments of stellar life. That confirmation arrived in a spectacular and unexpected fashion with the detection of a supernova designated as being within gamma-ray burst 250314 alpha. This was not just any explosion. It was the death cry of a star that lived when the universe was a mere 730 million years old. To put that into perspective, the universe today is 13,800 million years old. We are looking at a pinpoint of light from a time when the cosmos was barely 5% of its current age. This discovery has sent shockwaves through the scientific community because it represents the first time we have ever witnessed the death of an individual star from the true dawn of light. The sheer scale of the distance involved is staggering. Light travels at approximately 300,000 kilometers per second. In 1 year, light covers a distance of nearly 10 trillion kilometers. When we say this supernova occurred 13 billion years ago, we are describing a distance so vast that the numbers lose their meaning. The light we are seeing today left that dying star long before the Earth existed, long before our solar system was even a cloud of dust, and long before the Milky Way had taken its familiar spiral shape. It has spent the entire history of the world racing toward us, crossing through empty voids, and passing through the gravitational shadows of entire clusters of galaxies. The fact that a single telescope, floating 1,500,000 kilometers from Earth, could capture this specific, fleeting moment of destruction is a testament to human ingenuity. The cosmic dark ages ended when these first stars began to reionize the universe. Before their arrival, the space between atoms was filled with neutral gas that acted like a thick, opaque fog. The intense ultraviolet radiation from the first stars acted like a blowtorch, stripping electrons from hydrogen atoms and turning the fog into a transparent plasma. This process, known as reionization, was the most significant transformation in the history of the cosmos. It was the moment the universe became transparent. Without it, the light from distant objects would be scattered and absorbed, and the night sky would be a featureless gray. The supernova, detected by the James Webb Space Telescope, provides us with a direct probe into this transformative era. It is a lighthouse blinking from the edge of the world, offering us a rare glimpse into the conditions of the early universe. As we examine the data from this event, we are forced to confront the extreme nature of these early environments. The universe was smaller then, and matter was more densely packed. The first stars were born in environments of incredible purity, free from the carbon, oxygen, and iron that clutter the modern universe. Because they lacked these heavy elements, they could not cool down as easily as modern stars, which allowed them to grow to much larger sizes. A star that is 300 times the mass of our Sun would be unstable by today's standards, but in the early universe, these giants were the norm. They were the architects of the future, synthesizing the first heavy elements in their cores and then scattering them into space through the very supernova we are now beginning to observe. The detection of this supernova within a gamma-ray burst is particularly important because gamma-ray bursts are the most energetic explosions in the universe. They occur when a massive star collapses into a black hole or a neutron star, firing jets of radiation across the cosmos at nearly the speed of light. They are so bright that they can be seen from across the entire observable universe. However, finding the specific supernova associated with such a burst at this distance is incredibly difficult. It requires the telescope to be pointed at exactly the right spot at exactly the right time, and it requires the sensitivity to distinguish the fading afterglow of the supernova from the light of its host galaxy. The James Webb Space Telescope has achieved this, providing a level of detail that was previously thought impossible. This discovery is not just about a single explosion, it is about understanding the timeline of our existence. By observing the first stars and their deaths, we are looking at our own ancestry. Every atom of iron in your blood, every atom of calcium in your teeth, and every atom of oxygen you breathe was once inside the heart of a star. The heavy elements produced in the supernova of 730 million years after the Big Bang were the seeds for the stars and planets that would form billions of years later. We are made of star stuff, as the saying goes, and now we are finally seeing the very first generation of that star stuff being created. The shock that scientists feel is a mixture of awe and professional vindication. It confirms that our models of the early universe were largely correct, but it also shows that the universe was much more active and violent in its youth than we might have imagined. The silence of the Dark Ages was broken by these screams of light. Each supernova was a signal that the era of darkness was ending and the era of structure was beginning. Before these stars, the universe was a place of entropy and decay, a cooling remnant of the Big Bang. But with the arrival of the first stars, the universe began to build. It began to organize itself into galaxies and clusters. The supernova of the dawn of time is a marker of this transition. It represents the point where the laws of physics began to manifest in the form of complex objects. It is the beginning of the story that eventually leads to us. When the James Webb Space Telescope team released the announcement today, they emphasized that this is just the beginning. The telescope has enough fuel to operate for perhaps 20 years, and in that time, it will continue to peer deeper into the past. We are currently looking at a star that died 13 billion years ago, but there may be even older ones waiting to be found. The quest is to find the very first star, the one that broke the darkness for the first time. Such a discovery would be the ultimate prize in astronomy, the final piece of the puzzle. For now, the detection of this record-breaking supernova is the closest we have ever come. It is helpful to imagine the journey of those photons. For 13,000 million years, they traveled through a universe that was constantly changing. They passed by the formation of the first large galaxies. They witnessed the era when black holes began to grow into the monsters that sit at the centers of galaxies today. They survived the expansion of the universe, which sought to pull them apart and dim their energy. And finally, after a journey of inconceivable duration, they hit the gold-coated mirrors of the James Webb Space Telescope. In a fraction of a second, that ancient energy was converted into a digital signal processed by computers on Earth and presented to scientists as a beautiful, terrifying image of a star's final moment. The calm and steady gaze of the James Webb Space Telescope is our bridge to this era. While we live our lives in seconds, minutes, and hours, the telescope operates on a scale of millions and billions of years. It reminds us that we are part of a much larger narrative. The supernova from the dawn of time is a reminder of the fragility and the power of light. A single star, however massive, is a tiny speck in the vastness of the cosmos. Yet, its death was so powerful that we can still see it 13 billion years later. It is a message from a lost world, a world that existed before time, as we know it, had truly begun to unfold. As scientists continue to analyze the light from this event, they will look for the chemical signatures of the star's composition. They will look for evidence of how the first heavy elements were distributed into the surrounding gas. They will study the physics of the explosion itself to see if it differs from the supernova we see in the local universe. Each piece of data is a precious clue. The early universe was a laboratory of extreme physics, a place where gravity, radiation, and matter interacted in ways that we are still trying to model. This supernova is a direct observation from that laboratory, a data point that is more valuable than 1,000 simulations. The sense of peace that comes from this kind of exploration is profound. It reminds us that the universe has a history, a beginning, and a trajectory. We are not just floating in an eternal, unchanging void. We are part of a process that has been unfolding for nearly 14 billion years. The discovery of the most distant supernova ever seen is a milestone in that journey of understanding. It is a moment of clarity in a universe that is often confusing and overwhelming. By looking back to the dawn of time, we are finding our place in the grand design of the cosmos. We must also consider the technology that made this possible. The James Webb Space Telescope is a masterpiece of engineering. Its sunshield, the size of a tennis court, protects its sensitive instruments from the heat of the sun, allowing it to operate at temperatures close to absolute zero. Its mirror, composed of 18 hexagonal segments, acts like a giant bucket for light, catching the rarest photons from the deep past. Without these innovations, the light from the supernova of the dawn of time would have passed us by unnoticed and unrecorded. We would still be living in a world where the first stars were a mystery, a theoretical concept with no observational proof. The transition from the Dark Ages to the era of light was not an overnight event. It was a gradual process that took hundreds of millions of years. It was a time of competition between the dark gas and the nascent stars. But eventually, the stars won. They carved out bubbles of light in the darkness, and those bubbles grew and merged until the entire universe was illuminated. The supernova we are discussing today occurred toward the end of this process, when the first galaxies were already beginning to take shape. It is a witness to the final victory of light over shadow. In the coming hours, we will explore the specific mechanics of this detection. We will look at how the James Webb Space Telescope identifies these ancient signals among the millions of other objects in the sky. We will talk about the nature of gamma-ray bursts and why they are the perfect beacons for finding the first stars. But for now, let us simply reflect on the magnitude of what has been found. On this day, December 22nd, 2025, we have reached out and touched the very beginning of the world. We have seen a star die at the edge of time, and in doing so, we have learned a little more about how we came to be. The stillness of the universe today belies the violence of its past. When we look at the stars tonight, we are seeing the descendants of those first giants. The light we see with our eyes is young, perhaps only a few hundred or a few thousand years old. But behind that visible sky is the infrared sky, a realm of ghosts and echoes. The James Webb Space Telescope is the only instrument that can walk among those ghosts. It has found a ghost that is 13 billion years old, a star that exploded when the universe was still in its infancy. It is a discovery that shocks the mind and humbles the spirit, reminding us that the dawn of time is not just a concept, but a real physical place that we are finally beginning to see. To find a single dying star in the vast, teeming ocean of the cosmos is a task that borders on the miraculous. It requires not just the most advanced technology ever conceived by human hands, but also a profound degree of patience and a willingness to listen to the faint, fleeting whispers of the deep universe. The discovery that has so captivated the world began not with a steady image, but with a sudden, violent pulse of energy known as a gamma-ray burst. These events are the ultimate sirens of the cosmos, signaling the most extreme physical processes imaginable. On the 14th of March, 2025, a flash of high-energy radiation washed over our solar system, triggering sensors on satellites orbiting the Earth. This event, catalogued as Gamma-Ray Burst 20-50314 Alpha, was the opening act of a cosmic drama that would take months to fully comprehend. At the time, it was simply an alert, a set of coordinates in the constellation of the southern sky, but it held within it the secret of a star that had perished when the universe was still in its earliest youth. A gamma-ray burst is a phenomenon of terrifying power. It occurs when a massive star, far larger than our Sun, reaches the end of its life and collapses under its own gravity. In a matter of seconds, the core of the star vanishes, crushing itself into a black hole of immense density. As the star's outer layers fall inward toward this new abyss, they are caught in a magnetic maelstrom, launched outward in two narrow, focused jets that pierce through the dying star and scream into the vacuum of space. These jets travel at over 99% of the speed of light, carrying more energy in a few seconds than our sun will produce in its entire 10 billion year lifetime. If one of these jets happens to be pointed toward Earth, we see it as a brilliant, blinding flash of gamma rays. It is a lighthouse beam from the edge of reality, and for a brief moment, it becomes the brightest thing in the observable universe. When the alert for this specific burst was received, the astronomical community sprang into action. While gamma rays are invisible to the human eye, they provide a precise location for telescopes to follow. The challenge with these events is their brevity. The initial flash often lasts only a few seconds, while the subsequent afterglow, the fading light caused by the jets slamming into the surrounding interstellar gas, might last for days or weeks. To truly understand what happened, scientists needed to point the James Webb Space Telescope at those coordinates before the light vanished forever. This is no simple feat. Moving a massive telescope in deep space requires careful planning and the synchronization of dozens of systems. Yet, because of the potential importance of this specific signal, the telescope was diverted from its scheduled observations to stare into the fading embers of this ancient explosion. As the weeks and months passed, the data began to reveal something extraordinary. Usually, when we see a gamma ray burst from the very early universe, we are only seeing the jet of radiation itself. The star that produced the burst remains a mystery, hidden behind the blinding glare of the afterglow. But as the afterglow of gamma ray burst 250314 alpha began to dim, a second, softer glow emerged in the infrared data. This was the signature of the supernova itself, the actual explosion of the star's remains. In the local universe, seeing a supernova is common, but at these extreme distances, it was thought to be impossible. The light from a single star, even an exploding one, is usually far too faint to be distinguished from the light of its host galaxy. However, the James Webb Space Telescope, with its unparalleled sensitivity to infrared light, was able to isolate this specific glow. It was the first time in history that humans had directly observed the supernova of an individual star from the era of the first galaxies. The distance to this event was confirmed by measuring the stretching of its light, a phenomenon known as cosmological redshift. Because the universe has been expanding for 13 billion years, the space through which the light travels is literally being pulled apart. This causes the light waves to stretch, shifting them from the visible and ultraviolet parts of the spectrum into the deep infrared. By measuring exactly how much the light had been stretched, scientists determined that the explosion occurred 730 million years after the Big Bang. This places the supernova in the middle of the epoch of reionization, a time when the universe was transitioning from a cold, dark place into a cosmos filled with light and complex structures. The star we are seeing was a pioneer, one of the first generation of giants to live and die in the wilderness of the young universe. The shock felt by the scientific community stems from the fact that this star was even visible at all. To see an individual object from 13,000 million years ago requires a perfect alignment of circumstances. The star must have been incredibly massive, and the explosion must have been exceptionally luminous. There is also the possibility of gravitational lensing, where the mass of a foreground galaxy acts like a magnifying glass, boosting the light of the distant supernova. But even without such an assist, the detection of this event proves that the James Webb Space Telescope is capable of probing the universe in ways we had only dreamed of. We are no longer just looking at the collective light of billions of stars in a distant galaxy. We are looking at the final moments of a single, solitary sun. This specific supernova belongs to a class of explosions known as a hypernova. These are events where the energy released is 10 to 100 times greater than a standard supernova. In the early universe, where stars could grow to sizes that would be impossible today, these hypernova were likely the primary way that heavy elements were distributed. Inside the core of this ancient star, the immense pressure and heat were fusing hydrogen into helium, and then helium into carbon, oxygen, and neon. In the final seconds before the collapse, the star began to forge iron, an element that effectively poisons a stellar core because its fusion consumes energy rather than releasing it. When the core finally gave way, the resulting explosion not only created even heavier elements like gold and uranium, but also blasted them into the surrounding space at thousands of kilometers per second. The light we are seeing today is the visual record of that catastrophic enrichment. The process of analyzing this signal is one of extreme delicacy. Astronomers must subtract the light of the host galaxy and the fading remnants of the gamma-ray burst jets to find the true shape of the supernova's light curve. This curve tells us how the explosion brightened and faded over time, which in turn reveals the mass and composition of the star. Early results suggest that this star may have been over 200 times the mass of our Sun. Such a star is a monster by modern standards. In our own Milky Way, stars rarely exceed 100 solar masses, and those that do are highly unstable. But the early universe was different. It was composed almost entirely of hydrogen and helium, which made the gas clouds more resistant to fragmentation. This allowed enormous amounts of matter to pile up in one place, creating the first generation of stellar titans. The detection of this supernova is like finding a single glowing coal in a vast, dark forest. It tells us not just about the coal itself, but about the environment in which it burned. By studying the light as it passed through the gas of the early universe, scientists can determine how much neutral hydrogen was still present at that time. Each photon from the supernova had to navigate a minefield of gas clouds on its way to Earth. If it encountered a cloud of neutral hydrogen, certain wavelengths of its light would be absorbed, leaving a characteristic fingerprint in the spectrum. The data from December 22, 2025 shows that the universe was already becoming quite transparent by 730 million years after the Big Bang. But there were still pockets of the old primordial fog remaining. There is a certain irony in the fact that we use the most violent events in nature to learn about the history of peace and structure. A supernova is the ultimate act of destruction, yet it is also the ultimate act of creation. Without these explosions, the universe would be a boring, featureless place. It would be a cosmos of gas and nothing else. The supernova of the dawn of time was a vital step in the process of making the universe habitable. It provided the chemical building blocks for the second and third generations of stars, which would eventually host planets and, in at least one case, life. When we look at this signal from the edge of time, we are looking at the furnace in which our own existence was prepared. The James Webb Space Telescope team spent months verifying their findings before the announcement today. They had to be absolutely sure that what they were seeing was indeed a supernova and not just a variation in the brightness of the distant galaxy or an artifact of the telescope's instruments. They used multiple instruments, including the near-infrared spectrograph and the mid-infrared instrument, to capture different aspects of the light. Each instrument provided a piece of the puzzle. The spectrograph, in particular, was crucial, as it allowed them to see the specific chemical signatures of the ejecta, the material thrown out by the explosion. They found traces of oxygen and magnesium, elements that could only have been formed inside a massive star. This was the smoking gun that confirmed the nature of the event. As we move forward in our understanding, we must also appreciate the sheer loneliness of this star. It lived in a universe that was much smaller than ours, yet it was surrounded by vast, empty spaces. The first galaxies were not the grand spirals we see today. They were small, messy, and disorganized clumps of stars. This star likely sat in one of those early clusters, burning through its fuel with a frantic intensity. Its life was short, perhaps only a few million years, which is a mere heartbeat in cosmic terms. Our own sun has been burning for 4,500 million years and is only halfway through its life. The star from the dawn of time was a candle that burned at both ends, providing a brief but brilliant flash before disappearing into the void. The significance of the date of the announcement, December 22nd, is also noteworthy. It marks nearly 4 years since the launch of the James Webb Space Telescope on Christmas Day, 2021. In those 4 years, the telescope has rewritten much of what we thought we knew about the early universe. It has found galaxies that are older and more developed than models predicted, and now it has found the first individual supernova. Each of these discoveries pushes the boundary of our knowledge a little further into the past. We are slowly filling in the blanks of the cosmic calendar, moving closer and closer to the very first moment of the Big Bang itself. For the scientists involved, the detection of gamma-ray burst 250314 alpha was a moment of pure adrenaline, followed by months of quiet, meticulous work. There is a specific kind of tension that comes with observing a transient event. You know that the light is fading every second, and you have only one chance to capture the data. If the telescope had been pointed a few days later, or if the sensitivity had been slightly lower, this discovery might have been lost. The success of this observation is a tribute to the team that manages the telescope's schedule, a group of people who must balance the competing demands of thousands of astronomers while remaining ready to react to sudden cosmic events. This discovery also highlights the international nature of modern science. The James Webb Space Telescope is a collaboration between NASA, the European Space Agency, and the Canadian Space Agency. The satellites that first detected the gamma-ray burst are operated by multiple nations. The astronomers who analyze the data come from universities and research institutes all over the world. This is a truly global effort to understand our place in the universe. It reminds us that, despite our differences on Earth, we share a common curiosity and a common history. The Iwa star that exploded 13 billion years ago does not belong to any one nation. It is part of the heritage of all humanity. As the night deepens and we continue our journey through the cosmos, let us keep the image of this ancient signal in our minds. It is a tiny point of light, no brighter than a single pixel on a computer screen, but it contains the history of an entire world. It is a signal from the edge of time, a messenger from an era that we are only just beginning to explore. It tells us that the universe was active and violent and beautiful from the very start. It tells us that light will always find a way to travel across the darkness, no matter how vast the distance. And it tells us that we, with our telescopes and our curiosity, have the power to reach out and touch the very beginning of everything. In the next section, we will look more closely at the star itself. We will imagine what it would have been like to stand in its presence and what its death meant for the space around it. We will explore the physics of these primordial giants and why they were so different from the stars we see today. But for now, let us simply listen to the fading echo of that 13-billion-year-old explosion, a signal from the dawn of time that has finally reached our shores. To visualize the star that created the explosion, known as Gamma Ray Burst 250314 Alpha, one must abandon almost everything they know about the modern night sky. We live in a universe that is seasoned and complex, a place where stars come in a staggering variety of sizes, colors, and ages. But the star that the James Webb Space Telescope has just revealed was a member of the first generation, a breed of celestial giants that was fundamentally different from anything that exists today. These were the first suns, the true progenitors of light, born in a time when the universe was composed of only the most basic ingredients. They were the architects of the material world, and their death was as significant as their birth. As we look at the data released on this 22nd of December, we are not just seeing a distant flash, we are examining the anatomy of a primordial titan that stood at the very beginning of the chemical history of the cosmos. The first generation of stars, which astronomers refer to as population 3 stars, were born from the pure, unpolluted gas left behind by the Big Bang. For the first few 100 million years, the universe contained only hydrogen, helium, and trace amounts of lithium. There was no carbon for life, no oxygen for water, and no iron for the cores of rocky planets. In the modern universe, stars are polluted by these heavier elements, which astronomers collectively call metals. These metals play a crucial role in how stars are born. They act as coolants, allowing vast clouds of gas to radiate away heat and fragment into many smaller pieces. This is why the stars we see tonight, like our own sun, are relatively small and stable. But in the early universe, there were no metals to provide this cooling. The primordial gas clouds remained hot and bloated, and they could only collapse under their own weight if they were incredibly massive. The result was the creation of stars that were hundreds, perhaps even thousands, of times more massive than the Sun. The individual star that perished 730 million years after the Big Bang was likely one of these behemoths. If you could have placed this star in the center of our solar system, its surface would have extended far beyond the orbit of Jupiter, swallowing the inner planets in an instant. It was a violet-white orb of such intense radiation that it would have appeared blindingly bright even from billions of kilometers away. These stars were not the steady, long-lived companions we are used to. They were high-pressure forges, burning through their nuclear fuel at a rate that is difficult to comprehend. While a star like our Sun might simmer for 10 billion years, these primordial giants roared for only a few million years before their internal engines began to fail. The death of such a massive star is an event of unimaginable violence, and the detection of this supernova suggests it followed a path known as a collapsar model. Because the star was so massive, its internal gravity was a crushing force that was constantly trying to pull the star into a single point. For its short life, the outward pressure from nuclear fusion in its core managed to hold this gravity at bay. But as the star exhausted its hydrogen and began to fuse heavier and heavier elements, the core became increasingly unstable. When it finally attempted to fuse iron, the energy balance was lost. In a fraction of a second, the core collapsed, not into a solid object, but into a black hole. This newborn abyss immediately began to feed on the surrounding layers of the star, creating the powerful jets of energy that resulted in the gamma-ray burst detected earlier this year. However, the supernova itself is the story of what happened to the rest of the star's mass. As the core collapsed, a massive shock wave was sent racing outward through the star's outer layers. This shock wave was so powerful that it triggered a final runaway round of nuclear fusion, creating the heavy elements that the star had not yet forged in its core. It then blasted those outer layers into space at a significant fraction of the speed of light. This is the supernova that the James Webb Space Telescope has observed. It is a shell of expanding gas, trillions of kilometers wide, glowing with the heat of 1 billion suns. The shock that scientists are feeling today comes from the realization that we are seeing the specific chemical signatures of this debris. We are seeing the first time that oxygen, carbon, and silicon were ever introduced into that particular corner of the universe. This specific event, SN in GRB 250314, alpha, is a window into the process of chemical enrichment. Before this star exploded, the space around it was chemically empty. After the explosion, that space was filled with the building blocks of the future. Every generation of stars that followed this one would be born from gas that was slightly more complex, slightly more metallic than the gas before it. We are the distant descendants of this process. The carbon in your DNA and the iron in your blood were forged in the hearts of stars just like this one, billions of years ago. By observing the death of a star from 730 million years after the Big Bang, we are seeing the literal birth of the elements that make life possible. It is a profound connection across 13 billion years of time and space. The physics of these early stars also tells us something about the structure of the early universe. Because they were so hot and massive, they emitted vast amounts of ionizing radiation. This radiation was what cleared the neutral hydrogen fog of the Dark Ages, making the universe transparent. A single star of this magnitude could carve out a bubble of clear space millions of kilometers across. When you consider that there were millions of these stars forming in the first galaxies, you can begin to see how the dawn of time was not a quiet sunrise, but a violent, energetic transition. The supernova observed by the James Webb Space Telescope was a major contributor to this process. Its explosion did not just scatter elements, it sent out a final, massive pulse of radiation that helped to ionize the surrounding gas for thousands of light years in every direction. Scientists are particularly interested in whether this star was a solitary giant or part of a small, tight cluster. In the early universe, stars often formed in small groups within the first disorganized galaxies. If this star had siblings, its explosion would have had a dramatic effect on them. The shockwave would have compressed nearby gas clouds, potentially triggering the birth of a second generation of stars. Conversely, the intense radiation might have stripped away the gas from which other stars were trying to form, stunting their growth. The data from the James Webb Space Telescope is being scrutinized to see if there are any signs of these neighboring stars, or if this giant was a lonely sentinel in the dark. The scale of this star's death also challenges our understanding of black hole formation. When a star this large collapses, the resulting black hole is already quite massive, perhaps 30 or 40 times the mass of our Sun from the moment of its birth. This provides a potential answer to one of the biggest mysteries in astronomy. How did supermassive black holes grow so large so quickly in the early universe? If the first generation of stars left behind a population of substantial seed black holes, those seeds could have merged and fed on gas to become the monsters that we see at the centers of galaxies today. The supernova of the dawn of time is a glimpse into the starting line of this gravitational race. We must also reflect on the visual nature of this event. If you could have been there at a safe distance of several hundred light years, the supernova would have been the most incredible sight in the universe. For several weeks, it would have outshone the entire galaxy in which it resided. It would have changed from a brilliant blue-white to a deep, glowing red as it expanded and cooled. The surrounding gas clouds would have been illuminated like a cosmic firework display, glowing with the energy of the explosion. It was a moment of supreme beauty, even if there were no eyes in the universe to see it. Now, 13 billion years later, the James Webb Space Telescope has become those eyes, capturing the faint, red-shifted echo of that magnificent light. The composition of this star, being almost entirely hydrogen and helium, meant that it burned with a temperature that is almost impossible to find in the modern universe. Its surface temperature would have been in excess of 50,000 degrees, while our Sun is a relatively cool 5,500 degrees. This extreme heat meant that its light was concentrated in the ultraviolet spectrum. If it were not for the expansion of the universe, stretching that light into the infrared, we would never have been able to see it. The James Webb Space Telescope is effectively a heat-seeking camera, looking for the warmth of an explosion that happened at the beginning of time. There is a certain sadness in the short lives of these first stars. They were the pioneers of the universe, the ones who did the hard work of creating the first light and the first elements, yet they never lived to see the fruits of their labor. They died long before the first stable galaxies formed and long before the first planets were born. They were a transient population, a bridge between the simplicity of the Big Bang and the complexity of the modern world. The supernova we are observing today is the final act of one of these pioneers. It is a signature of a lost era, a time when the universe was ruled by giants that were destined to vanish. The James Webb Space Telescope's ability to distinguish this individual supernova from the light of its host galaxy is a feat of precision. The host galaxy, 730 million years after the Big Bang, was likely a small, irregular clump of a few million stars. To the telescope, it appears as a tiny, faint smudge. But by using its spectrographs, the telescope could see that a specific part of that smudge was getting brighter and then fading over several months. By analyzing the light from that specific point, they could see the signature of the expanding shell of the supernova. It is like seeing a single candle flicker in a distant, foggy window from kilometers away. As the analysis continues, scientists will look for signs of pair instability, supernovae. This is a theoretical type of explosion that only happens to stars between 140 and 260 times the mass of the Sun. In these stars, the core becomes so hot that gamma rays are converted into pairs of electrons and positrons. This causes a sudden drop in pressure, leading to a catastrophic collapse and a massive explosion that leaves absolutely nothing behind. No black hole, no neutron star, just a cloud of elements. If SN in GRB 250314 alpha was one of these, it would be a major discovery, as no such explosion has ever been definitively observed in the local universe. It would prove that the first generation of stars truly operated by a different set of rules. The death of this primordial giant was not the end, but a beginning. The shock waves it sent through the early universe are still, in a sense, echoing today. They set the stage for everything that followed. The discovery announced on this 22nd of December is a reminder that the universe has a memory. The light carries the information of what happened, and if we are clever enough to build the right tools, we can retrieve that memory. We can learn about the first stars, their incredible scale, their pure composition, and their violent deaths. We can see the dawn of time as a real physical era populated by real physical objects. The calm, steady narration of the James Webb Space Telescope's data provides us with a sense of perspective. We are part of a cosmic cycle of birth, death, and rebirth. Stars die so that new stars can be born from their remains. Galaxies merge and grow. Planets form in the debris of ancient explosions. The most distant supernova ever seen is a link in this chain, a vital part of the story that leads to our own existence. As we move into the next section of our journey, we will follow the path that this light took through the universe, crossing 13 billion light years to reach our mirrors. We will explore the vast, expanding void that separates us from the dawn of time. But for now, let us hold on to the image of the star itself, a violet giant, burning with the fury of a billion suns, standing alone in the darkness of the early universe. Its death was a scream of light that has traveled across the entirety of cosmic history to reach us. It is a testament to the power of the stars and the persistence of light. It is a primordial giant, finally seen, finally understood, and finally given its place in the history of the universe. The dawn of time is no longer a shadow. It is a landscape, and this star was one of its most magnificent features. To understand the discovery of the supernova within gamma ray burst 250314 alpha, we must look beyond the explosion itself and contemplate the extraordinary journey of the light it produced. When that massive star collapsed and erupted 730 million years after the Big Bang, it released a torrent of photons that began a flight through the vacuum of space that would last for over 13 billion years. This journey is one of the most remarkable stories in all of science, for it involves not just the passage of time, but the literal stretching of the fabric of reality. The light we see today is not the same light that left the star. It has been transformed by its passage through an expanding universe, carrying with it a record of everything it encountered along the way. As we follow these photons across the infinite void, we gain a deeper appreciation for the scale of the cosmos and the unique capabilities of the James Webb Space Telescope. When the photons first escaped the dying star, they were energetic and violent. In the heart of a supernova, the temperatures are so extreme that the light is emitted as high-energy gamma rays and ultraviolet radiation. If you had been standing nearby, this light would have been invisible and deadly, a silent wave of radiation capable of stripping the atmosphere from a planet. But as these photons began their journey, they immediately entered a universe that was much smaller and denser than the one we inhabit today. At that time, the galaxies were closer together, and the space between them was still being cleared of the primordial gas left over from the Big Bang. The light from our supernova had to navigate this crowded, infant world, passing through the shadows of the first infant galaxies and dodging the gravitational wells of massive clouds of dark matter. However, the most significant influence on the light was not the matter it passed, but the space through which it traveled. We often think of space as an empty container, a passive stage on which the drama of the universe unfolds. But Einstein taught us that space is a dynamic fabric, capable of bending, warping, and, most importantly, expanding. Ever since the Big Bang, the universe has been growing, with the distance between galaxies increasing every second. As the photons from the supernova moved through this expanding space, the waves of light were literally stretched along with the fabric of the cosmos. This phenomenon, known as cosmological redshift, is the reason why we need a specialized instrument like the James Webb Space Telescope to see the early universe. Imagine a wave of light as a vibrating string. When it left the supernova 13 billion years ago, it was vibrating very rapidly, with a short wavelength that placed it in the ultraviolet part of the spectrum. But as it traveled through millions and then billions of light years of expanding space, the string was pulled longer and longer. By the time it had traveled halfway across the universe, it had been stretched into visible blue light. By the time it reached the era of the first dinosaurs on Earth, it had become a dull red. And by the time it finally arrived at our solar system in December 2025, it had been stretched into the long, invisible wavelengths of the mid-infrared. The light has become a deep, low-frequency echo of its former self, a ghost of a signal that can only be felt as heat. The scale of this journey is truly mind-bending. During the 13 billion years that this light was in transit, the entire history of our world unfolded. When the light was halfway to Earth, our Milky Way galaxy was still a disorganized clump of gas and older stars. When the light was 90% of the way here, a cloud of dust and gas in a quiet corner of the galaxy began to collapse to form our Sun and its planets. For the last 4,500 million years, while life was evolving from single cells into complex organisms, these photons were still racing across the final stretch of the void. They passed the orbits of distant stars, crossed the threshold of our solar system, and finally, after a journey of inconceivable duration, they struck the gold-coated mirrors of the James Webb Space Telescope. The telescope itself is stationed at a unique point in space called the second Lagrange point, located 1,500,000 kilometers away from Earth. This location was chosen specifically because it is far enough from the heat and light of our planet to allow the telescope to remain incredibly cold. To detect the stretched infrared light from a 13 billion-year-old supernova, the telescope must be kept at a temperature of -233 degrees Celsius. If it were any warmer, the telescope's own heat would wash out the faint signal from the dawn of time. The gold on the mirrors is not for decoration. Gold is one of the best reflectors of infrared light, ensuring that almost every precious photon from the ancient supernova is captured and directed into the instruments. This journey through the void also provides us with a way to measure the expansion of the universe itself. By comparing the distance the light has traveled with the amount it has been stretched, astronomers can calculate the rate at which the universe is growing. This is a vital piece of the puzzle in understanding dark energy, the mysterious force that is causing the expansion to accelerate. The supernova from 730 million years after the Big Bang acts as a standard candle or a fixed point in the distance. Because we understand the physics of how these stars die, we can estimate how bright the explosion should have been at the source. By measuring how dim it appears today, we can determine exactly how much the universe has grown in the time it took for the light to reach us. However, the journey was not always a straight line through an empty vacuum. Gravity has the power to bend light, a process known as gravitational lensing, As the photons from the supernova traveled toward Earth, they occasionally passed near massive objects like large galaxies or clusters of dark matter. These objects warped the space around them, acting like a lens that could focus or distort the light. In some cases, this lensing can make a distant object appear much brighter than it actually is, acting as a natural telescope. Scientists are currently investigating whether the light from gamma ray burst 250314 alpha was boosted by such a lens, which might explain why we were able to see the individual supernova so clearly across such a vast distance. The light also carries a chemical record of its journey. As it passed through the intergalactic medium, the thin gas that fills the space between galaxies, some of its wavelengths were absorbed by atoms of hydrogen, helium, and heavier elements. By analyzing the gaps in the spectrum of the light, astronomers can map the distribution of matter in the early universe. They can see where the first clouds of gas were located and how the first heavy elements were beginning to spread. The photons are like messengers that have stopped at every station along the way, picking up information and carrying it to us. The data released today is not just an image of an explosion. It is a map of 13 billion years of cosmic geography. It is also worth considering the psychological impact of this journey. We are looking at a star that has been dead for 13,000 million years. In a very real sense, the star does not exist anymore, and has not existed for almost the entire duration of the universe's life. We are looking at a memory, a visual echo of a past that has long since vanished. This is the profound paradox of astronomy. The further we look into space, the further we look back in time. The dawn of time is not just a poetic phrase, it is a physical location in the deep sky. By capturing this light, we are reaching across the infinite void to touch a moment that occurred before the concept of Earth even existed. The silence of the journey is also something to contemplate. For 13 billion years, these photons traveled in absolute silence through the most perfect vacuum imaginable. They were not disturbed by the noise of worlds or the turbulence of atmospheres. They were a pure, undisturbed signal, a beam of information preserved in the cold of space. The fact that we have built a machine capable of intercepting that signal and translating it into something we can understand is a triumph of the human spirit. It shows that we are not just passive observers of our small corner of the world, but active participants in the life of the entire cosmos. The James Webb Space Telescope's detection of this supernova is a reminder of how much of the universe remains invisible to our eyes. If we were to look at the same spot in the sky with a standard optical telescope, we would see nothing but blackness. The light is there, but it is vibrating too slowly for us to perceive. The universe is full of these hidden signals, messages from the past that are passing through our bodies every second. The telescope acts as a translator, bringing these invisible stories into the light. It allows us to see the invisible universe that was described in the earlier explorations of our channel. As the photons entered the telescope's instruments, they were processed by a series of mirrors and filters before hitting a sensitive detector. Each photon was converted into a tiny electrical charge, which was then digitized and beamed back to Earth via a network of deep space antennas. This final step in the journey took only a few seconds, a mere blink of an eye compared to the 13 billion years of travel that preceded it. From the second Lagrange point, the data traveled to the Deep Space Network stations in Australia, Spain, and California, and then on to the Space Telescope Science Institute in Baltimore. There, it was transformed into the images and spectra that have shocked the world today. Scientists often speak of the observable universe, which is the sphere of space from which light has had time to reach us. The supernova, from 730 million years after the Big Bang, is near the very edge of this sphere. Beyond it, there are regions of space from which the light is still traveling, or from which the light will never reach us because the expansion of the universe is pulling those regions away faster than the speed of light. By finding this supernova, we have pushed the boundary of our direct observations even closer to the ultimate horizon. We are seeing into the very furthest reaches of our cosmic home. The journey of the light from SN in GRB 250314 alpha is a testament to the persistence of energy. A star lived for a few million years, exploded in a magnificent burst of power, and then spent 13 billion years sending a message of its existence across the void. It is a story of survival against the impossible odds of expansion, absorption, and time. The fact that the message was finally received is a cause for celebration. It confirms that the universe is a coherent whole, a system where the past and the present are connected by the simple, unwavering flight of photons. In the next section, we will explore the aftermath of this journey, how this specific explosion helped to shape the early universe and clear the cosmic fog. We will look at the physical changes that occurred in the space around the star, and how those changes allowed the universe to become the transparent, light-filled place we see today. But for now, let us reflect on the flight itself. 13 billion years of travel across an expanding void, ending in a single moment of detection. It is a journey that humbles us, reminding us of the vastness of the stage on which our lives are played. The light from the dawn of time has finally reached us. It has crossed the infinite red-shifted void to tell us its story. It is a story of a star's death, but also a story of the universe's growth. It is a signal of hope, showing us that no matter how dark or distant the past may seem, the light will always find a way to reach the future. While the light from the supernova within gamma ray burst 250314 alpha tells a story of a journey across time, the physical consequences of the explosion itself tell a story of a universe being remade. To understand why this discovery has so profoundly moved the scientific community, we must look at what happened in the immediate vicinity of that star 13 billion years ago. This was not merely a spectacular firework display in the dark. It was a fundamental act of cosmic engineering. Every supernova in the early universe was a catalyst for change, a violent but necessary step in the transformation of the cosmos from a simple cold cloud of gas into the vibrant and complex garden of galaxies we inhabit today. By observing this specific event from 730 million years after the Big Bang, we are witnessing a crucial moment in the clearing of the primordial cosmic fog and the seeding of the elements that would eventually define the nature of life itself. In the era before these first giants began to die, the universe was a place of extreme chemical simplicity. As we have discussed, it was composed almost entirely of neutral hydrogen and helium. This gas was not just a passive background, it was an opaque veil. During the period known as the Dark Ages, the universe was filled with this neutral hydrogen, which is incredibly effective at absorbing and scattering certain types of light, particularly ultraviolet radiation. This created a literal fog that made the early universe murky and dark. For the first few 100 million years, the light from the very first stars was trapped, unable to travel far before being swallowed by the surrounding neutral gas. The transition from this state to the transparent universe we see today is known as the epoch of Rayonization, and the supernova of the dawn of time was one of the primary drivers of this change. When our massive star exploded, it did not just release light, it released an unimaginable amount of kinetic energy and ionizing radiation. The shock wave from the explosion tore through the surrounding primordial gas at thousands of kilometers per second, heating it to millions of degrees and stripping electrons away from their parent hydrogen nuclei. This process of stripping electrons is what we call ionization. Once the hydrogen atoms were ionized, they were no longer able to absorb and scatter ultraviolet light in the same way. The explosion effectively blew a hole in the cosmic fog, creating a bubble of transparent space that extended for tens of thousands of light years in every direction. Each supernova was like a match being struck in a smoke-filled room, slowly but surely clearing the air. By 730 million years after the Big Bang, these bubbles were beginning to overlap and merge. The data from the James Webb Space Telescope allows us to see this transition in real time. Because we can analyze the light from the supernova as it passed through the gas in its local neighborhood, we can measure exactly how much of that gas had already been cleared and how much remained in its neutral, foggy state. The discovery of this event provides a snapshot of the final stages of Rayonization. It shows us a universe that was becoming clear, where the light from distant objects was finally able to begin its long journey across the cosmos without being immediately absorbed. It is the record of the universe waking up and becoming visible to itself. But the role of the supernova was not limited to clearing the fog. It was also the primary source of chemical alchemy. Before these explosions, there was no solid matter in the universe. There were no grains of dust, no pebbles, and certainly no rocky planets. There was only gas. Inside the heart of our dying star, the extreme pressure of its final collapse forged the first heavy elements. When the star exploded, it scattered these elements, carbon, oxygen, magnesium, and silicon, into the surrounding space. These were the first impurities in a pristine universe. These heavy elements changed the way that gas clouds cooled and collapsed, allowing the next generation of stars to be smaller, more numerous, and more stable. The supernova we are studying today was a gardener, tilling the cosmic soil and adding the nutrients that would allow the future to grow. This chemical enrichment was a slow and iterative process. A single supernova could only pollute a small region of space, but over millions of years and millions of explosions, the entire composition of the universe began to shift. We can see the signatures of these elements in the spectrum of the supernova's light. The presence of oxygen and magnesium in an explosion that occurred so early in time is a powerful confirmation of our models of stellar evolution. It tells us that by 730 million years, the process of making the universe metal-rich was already well underway. This provides a direct link between the first generation of giants and the world we know today. Without the violent deaths of these primordial stars, the chemistry of life would never have existed. The energy from the supernova also played a dual role in the formation of new stars, a process known as stellar feedback. On one hand, the immense heat and radiation could be destructive. The blast could blow away the gas from which smaller stars were trying to form, effectively stunting the growth of its home galaxy. This negative feedback acted as a cosmic brake, preventing galaxies from turning all of their gas into stars too quickly. On the other hand, the shock wave from the supernova could also be a creative force. As it slammed into distant cold clouds of gas, it would compress them, triggering a new wave of star formation. The death of one star could, in a very real sense, spark the birth of 1,000 others. The supernova of the dawn of time was a pulse of energy that rippled through the infant galaxy, dictating which stars would live and which would never be born. This discovery also allows us to study the physics of the intergalactic medium during this transformative era. The space between galaxies was not empty. It was a web of gas and dark matter that connected the first structures. The light from the supernova had to travel through this web, and as it did, it was shaped by the temperature and density of the gas it encountered. By studying the specific patterns of absorption in the light, scientists can create a three-dimensional map of the environment surrounding the host galaxy. They can see the filaments of the cosmic web beginning to take shape, and the first large-scale structures of the universe being carved out by the energy of dying stars. There is a sense of immense power in these early explosions. A hypernova like the one associated with gamma-ray burst 250314 alpha was so energetic that it could influence the evolution of an entire small galaxy. In the modern universe, a single supernova is a local event, affecting only a small part of a spiral arm in a massive galaxy like the Milky Way. But in the early universe, galaxies were tiny and fragile. An explosion of this magnitude was like a volcanic eruption in a small village. It reshaped everything. It altered the gravitational balance of the galaxy, redistributed its mass, and changed its chemical future. We are looking at a moment of supreme influence, where the actions of a single star had consequences that reached across millions of parsecs. The scientific community is particularly intrigued by the timing of this event. 730 million years after the Big Bang is often considered the peak of the ionization process. It is the tipping point where the universe moved from being mostly opaque to being mostly transparent. Finding a supernova at exactly this moment is like finding a photograph of the very moment a fog begins to lift. It allows us to test our simulations of reionization with unprecedented precision. Did the clearing happen in large, sudden bursts, or was it a gradual, steady process? The data from the James Webb Space Telescope suggests a complex, patchy reionization where certain regions were cleared much faster than others, likely due to the presence of massive, early dying stars like our own. We must also consider the role of the black hole that was left behind. While the outer layers of the star were blasted away to enrich the universe, the core remained as a dark, silent remnant. This black hole would have begun to feed on any gas that remained in its vicinity, becoming an even more powerful source of energy and further influencing the evolution of the galaxy. In the early universe, these stellar mass black holes were the building blocks of the supermassive black holes that would eventually dominate the centers of galaxies. The supernova was the transition point between a luminous giant and a dark gravity well. It was the moment a source of light became a source of shadows. The James Webb Space Telescope's ability to detect this event is a triumph of infrared astronomy. Because the ionization fog was so thick, visible light would have been scattered and lost. But infrared light, with its longer wavelengths, is much better at penetrating gas and dust. This is why we say that Webb can see through the cosmic fog. It allows us to peer into the heart of the epoch of ionization and witness the events that were previously hidden from our view. The discovery announced on December 22nd is the first time we have truly seen through the veil to identify the specific individual actors in this grand cosmic drama. As we analyze the fallout of this explosion, we are also learning about the speed of light and the speed of change. The physical shock wave from the supernova traveled much slower than the light, taking millions of years to cross the distances that the light crossed in an instant. While we see the light today, the physical consequences of that explosion are still playing out in that distant part of the universe. The elements scattered 13 billion years ago have since been incorporated into countless other stars and perhaps even planets. The region of space we are looking at has undergone billions of years of evolution since that star died. In a sense, the supernova was a first stone thrown into a pond, and we are seeing the very first ripple. The sense of peace and order we see in the universe today is built on this foundation of ancient chaos. The transparent sky, the variety of elements, and the stability of modern stars are all the result of the violent work done by the first generations. The supernova of the dawn of time was a worker in the cosmic factory, breaking down the old and building up the new. It was a moment of profound significance that helped to determine the physical laws of the universe we live in. By observing it, we are gaining a deeper understanding of the mechanisms of cosmic history. The narration of this discovery is also a narration of human progress. A century ago, we did not even know that other galaxies existed. 50 years ago, the first generation of stars was a purely theoretical concept. Today, we have an instrument that can reach across 13 billion years and capture the death of a single star. It is a reminder that our curiosity is a powerful force, one that allows us to overcome the vastness of space and the passage of eons. The discovery of the most distant supernova ever seen is a victory for everyone who has ever looked up at the stars and wondered where they came from. In the final section of our documentary, we will reflect on how this single discovery is rewriting the history of everything. We will look at how it changes our timeline of the early universe and what it means for the future of astronomy. We will consider the new questions it raises and the mysteries that still remain. But for now, let us reflect on the transformation. The cosmic fog is lifting, the first elements are being forged, and the universe is becoming a place of light and complexity. The supernova of the dawn of time was the fire that made it all possible. As the data continues to be processed by the world's leading astronomers, the image of this explosion will become even clearer. We will see the fine details of the chemical ejecta and the subtle echoes of the radiation. We will understand, with greater clarity than ever before, how our world was born in the depths of these ancient titans. The shock that scientists feel is not just about the distance. It is about the realization that we are finally seeing the foundation of our own reality. On this 22nd of December, 2025, we have witnessed the moment the universe began to change forever. As the news of the discovery of the supernova within gamma ray burst 250314 alpha continues to resonate across the globe on this December day, we find ourselves standing at a threshold where the history of our universe must be fundamentally rewritten. The announcement made by the National Aeronautics and Space Administration and the European Space Agency on December 22, 2025, is not merely a scientific update or a minor correction to an existing chart. It is a paradigm shift that challenges our most basic assumptions about how quickly the cosmos moved from its infancy into a state of violent, productive maturity. By capturing the death of an individual star from a time when the universe was only 730 million years old, we have unlocked a chapter of the cosmic story that was once thought to be permanently lost to the shadows of time. This single data point, a flicker of infrared light from 13 billion years ago, forces us to reevaluate the speed of stellar birth, the efficiency of early chemical forge, and the very nature of the first generation of suns. The shock felt by scientists in the wake of this detection stems from a realization that the early universe was far more developed and chemically active than many models had predicted. For decades, the consensus was that the first billion years were a slow and tentative period of assembly. We imagined the first stars forming in isolation, struggling to clear the vast clouds of primordial gas, and taking immense amounts of time to forge the heavy elements required for more complex structures. But the James Webb Space Telescope has presented us with a different reality: the existence of a massive supernova, already rich with signatures of oxygen and magnesium, so early in the timeline suggests that the cycle of stellar birth and death was already operating at a frantic pace. It implies that the universe did not slowly wake up, but rather erupted into activity, with generations of stars living and dying in a cosmic blink of an eye. This discovery moves the goalposts for our understanding of when the age of complexity truly began. This shift in perspective has profound implications for our search for the first stars, the elusive Population 3 giants. If we are already seeing the sophisticated death of a star 730 million years after the Big Bang, then the very first stars must have arrived much earlier than we once dared to hope. It suggests that the cosmic dawn was an even more ancient and energetic event, possibly beginning just a few hundred million years after the expansion of space began. Astronomers are now looking even further into the infrared, pushing the James Webb Space Telescope to its absolute limits to find the ancestors of the star we have just observed. We are no longer looking for a single moment of beginning, but rather a complex and ancient lineage of stars that were already old when our supernova exploded. The timeline of the universe has been stretched, and we are finding that the dawn of time is a much more crowded and busy era than we ever imagined. The chemical signatures captured by the telescope spectrographs are perhaps the most revolutionary part of this discovery. Until today, the transition from a universe of pure hydrogen to a universe filled with the elements of life was a process we could only simulate on computers. Now, we have a direct observation of that alchemy in action. The presence of heavy elements in the ejecta of a star 13 billion years ago tells us that the seeds for planets and life were being sown almost from the very start. It raises the tantalizing possibility that the conditions for rocky planets might have existed much earlier in cosmic history than we ever thought possible. While we do not expect to find life in these first violent galaxies, the fact that the building blocks were already being forged suggests that the universe has been life-friendly for almost its entire existence. The supernova of the dawn of time is a testament to the universe's incredible capacity for self-organization and creation. Furthermore, this discovery anchors our understanding of the epoch of reionization with a level of certainty that was previously unattainable. By providing a bright, localized source of light from 730 million years after the Big Bang, the supernova has acted as a probe, illuminating the gas that filled the space around it. The data shows that by this time, the bubbles of transparent space were already large and beginning to merge, but they were still surrounded by remnants of the primordial fog. This confirms that Ryanization was not a uniform event, but a patchy and chaotic transformation driven by the intense radiation of the first stars. We now have a physical marker in the timeline of this transformation, a way to calibrate our models and understand how the universe became the transparent, light-filled place it is today. It is a moment of clarity in a narrative that has been murky for generations of astronomers. The success of the James Webb Space Telescope in making this detection also marks a new era for the mission itself. In the 4 years since its launch, the telescope has exceeded every expectation, but the discovery of an individual supernova from 13 billion years ago is a milestone of a different order. It proves that the telescope's sensitivity and resolution are sufficient to isolate single objects at the very edge of the observable universe. This opens up a new field of high redshift stellar archaeology, where we can begin to study the individual lives and deaths of the stars that built the first galaxies. We are no longer limited to looking at the collective glow of billions of stars. We can now zoom in on the specific actors in the cosmic drama. The next 20 years of observations promise to be a journey of discovery that will take us even closer to the moment of the Big Bang, perhaps even to the birth of the very first star. As we reflect on the significance of December 22nd, 2025, we must also consider the human element of this story. The shock and awe felt by the scientists at the National Aeronautics and Space Administration and the European Space Agency is a reminder that we are still capable of being surprised by the universe. Despite our advanced technology and our complex theories, the cosmos still holds secrets that can leave us breathless. The image of the dying star, captured by a machine floating in the cold of space, is a bridge between our small, fleeting lives and the vast, eternal history of the universe. It reminds us that we are part of a narrative that began billions of years ago and will continue long after we are gone. Our curiosity is the flame that lights the way through the darkness, allowing us to reach out and touch the dawn of time. The calm and steady gaze of the James Webb Space Telescope has given us a gift of perspective. It shows us a universe that is both violent and beautiful, a place where destruction is the prerequisite for creation. The supernova of the dawn of time was a catastrophe for the star and its immediate surroundings, but it was a triumph for the universe as a whole. It was the moment that the first elements were scattered, the first fog was cleared, and the first steps toward our own existence were taken. We are made of the debris of stars like this one, and in observing its death, we are looking at our own ancient heritage. The connection across 13 billion years is not just a scientific curiosity, it is a fundamental truth about who we are and where we come from. In the quiet hours of this night, as we contemplate the depth of space and the passage of eons, the discovery of the most distant supernova ever seen provides a sense of peace. It confirms that the universe is not an incomprehensible void, but a place with a history that we can learn and understand. It tells us that light is a persistent messenger, carrying the stories of the past across the infinite void to reach our mirrors. No matter how vast the distance or how deep the shadow, the events of the early universe are not lost. They are waiting for us to find them. The invisible universe is becoming visible one star at a time, and with each new discovery, the darkness of our ignorance recedes just a little further. The future of astronomy after this discovery is one of immense potential. We are already planning for the next generation of telescopes, both on the ground and in space, that will build on the legacy of the James Webb Space Telescope. The extremely large telescope in Chile and the Nancy Grace Roman Space Telescope will provide even more data, allowing us to map the early universe with even greater precision. We will search for more gamma-ray bursts and more supernovae from the dawn of time, filling in the gaps in our cosmic calendar. We will look for signs of the first black holes and the first chemical ripples in the primordial gas. The journey of exploration that began centuries ago is entering its most exciting phase, and we are fortunate to be alive at a time when the secrets of the beginning are finally being revealed. We should also take a moment to appreciate the silence and the scale of the discovery. 13 billion years is a duration that the human mind cannot truly comprehend. It is the history of the world 10,000 times over. Yet, the information from that time is here, present in our computers and our minds. It is a reminder that we live in a universe of incredible permanence and incredible change. The star is gone. Its host galaxy has likely merged and transformed into something else entirely, and the space between us has grown by billions of light years. Yet, the light remains. It is a signal of the enduring nature of energy and the unwavering path of photons. It is a reminder that in the grand design of the cosmos, nothing is ever truly forgotten. The announcement today is a celebration of the power of science to illuminate the unknown. It is a tribute to the thousands of engineers, scientists, and technicians who dedicated their lives to building and operating the James Webb Space Telescope. It is a victory for the human spirit, showing that our desire to know and understand is stronger than the barriers of time and space. The supernova of the dawn of time is our reward for that dedication, a magnificent and terrifying image of the beginning of the world. It is a discovery that will be studied for decades, a foundational piece of evidence that will anchor our understanding of the universe for generations to come. As we end our journey tonight, let us remember the star that died so that we could see the beginning. Let us remember the light that traveled 13 billion years to reach us. And let us remember the curiosity that drives us to build telescopes and seek out the secrets of the stars. The universe is vast and ancient and full of mysteries, but we have proven that we are capable of reaching into the darkness and bringing the truth into the light. The dawn of time is ours to explore, and this is just the beginning.